Welcome to Give Students Science and Technology Physics class. I'm NC Joshua, popularly known as Oracle. Today we'll be looking at refraction of light. That's what we're looking at today. What's refraction? Refraction is the bending of a wave. So what is refraction of light? Is the bending of light when it goes from one medium to another medium. So a light traveling from air would definitely not continue in that same path and at that same speed when it goes into another medium. So the reason why the light is bending is because the wavelength of the wave is changing and the speed of the wave is changing. I reiterate again, the reason why the light wave is bending, is because the light has entered into a different medium. And so now some things are changing. And which are those? We have the wavelength of the light is changing, the speed of the light is changing, but the frequency of that light is constant. So in refraction, when light wave burns, there is one property of the wave that does not change. It is called the frequency. Now, this is the reason why when you stand in a pool, your legs appear shorter than it is. This is the reason, refraction is the reason why when you look at a deep pool, it appears as though it is shallow. Refraction is the reason why when you put a stick in a bowl of water, it appears bent instead of straight. Now, all of these reasons is because the light ray is traveling from one medium to another. Definitely, there must be a bending of the wave. Now, look at such cases we have on the board, or these cases we have on the board. We have light traveling from air to glass. Now, remember that the angle that the incident ray makes with the normal is called the incident angle. So this is the incident ray. So if this is the incident ray, then it means the angle, the normal, the angle, this is the refracted ray, this is the refracted ray. The angle the refracted ray mixed with the normal is called the refracted angle. So this is the incident angle, this is the refracted angle. This is the refracted ray, this is the incident ray. Now, what is happening in this case? Light is traveling from a less dense medium to a more dense medium. So when light travels from a less dense to a more dense, it burns towards the normal. But if you check the second example, it's bending away from normal. So it's traveling from a denser medium to a less dense medium. So I can have water and glass. Water is less dense than glass. So it will be as the same thing as air to glass. So when light travels from a less dense to a more dense, the light bends towards normal. But when it travels from a more dense to a less dense, more dense to a less dense, it bends away from normal. Less dense to more dense, it bends towards normal. But when light is shone normally, it goes unrefracted. Take note of that. When light is shone normally, it goes unrefracted. Now, what's the next thing I want you to see? The next thing I want you to see is what we call refractive index. Refractive index. But we will not know refractive index unless we understand the law of refraction. The law of refraction. What is the law of refraction? The first law of refraction states that the angle of incidence and the opposite angle of refraction both lie on the same plane. The angle of incidence and the opposite angle of refraction both lies on the same plane. Then what is the next law of refraction? The next law of refraction states that the sine of the angle of incidence ratio the sine of the angle of refraction is equals a constant. The sine of the angle of incidence to the ratio of the sine of the incident angle to the sine of the refracted angle is equal to a constant, and this constant is called refractive, index. That's what is called refractive index, and we use this to connect refractive index. So I cannot say that refractive index is equal sine incident over sine refracted angle. Take note of this. Now, it's not only this formula we can use to calculate for refractive index. Now, remember I told you that there are certain things that changes when light travels from one medium to another medium. One of the things that changes is speed, meaning I can solve number one. This is number one. I can do number two, how to calculate refractive index in terms of speed. Refractive index is speed in air over speed in medium. So I have the medium can be in water or in glass. So remember again, refractive index, let's see something like from air to glass. So it will be speed in air over speed in glass. Refractive index is speed in air over speed in glass. What about wavelength? In terms of wavelength, I have air to glass. Refractive index is wavelength in air over wavelength in glass. You see, it's the same way we use in expressing speed, we express wavelength. What about frequency? Remember, frequency is constant. The frequency of the light in air is equal to the frequency of the light in water. Frequency is always constant. What about number four? If I want to express refractive index in terms of refractive index. Now I want to check on refractive index in terms of refractive index. I will say the refractive index of air to glass is equal to the refractive index of glass over refractive index of air. Take note of this. If you watch, this is the first time it's alternated. It's unlike the other ones. Watch, from air to glass, speed of air over speed of glass. From air to glass, wavelength of air over wavelength of glass. But from air to glass, refractive index of glass over refractive index of air. Take note of this. That's how it is expressed. Now, the next case I would love to show you now is about this case here. Now, remember that light was incidented, and the light bent in this direction. Originally, this would have been the pathway of the light. So this would have been the way the light ought to go, but the light burned towards the direction, meaning this angle is called the angle of deviation. This angle here is called the angle of deviation. So now, what is angle of incidence equal to? Angle of incidence is equal to refractive angle plus angle of deviation. Take note of this. So it means that if I want to solve for angle of deviation, I will use the angle of incidence, which is this angle, equal these two angles here, which equals the refracted angle plus the angle of deviation. Take note of that. That's very, very important. Very, very important. Now, this ought to be, now let me show you something here. This ought to be a format of refraction in glass. Now, if light shines into this glass, it will bend, and when it gets here, it will go out. Now, remember, this is the incident. This is the incident ray. Is the incident ray. Incident ray. This here is the refracted ray. Let's write it here. This is the refracted A. Let me make it A, B, and C. A is incident ray. B is refracted ray. B is refracted ray. While C is your emergent emergent ray, that's C. So this is my angle of incidence, while this is my refracted angle, while this is my emergent angle. So this is my emergent ray, that is C, emergent ray. Now, this would have been the actual part of this. It would have been like this, never to meet with this guy. It will just be going parallel. So what is the gap between this and this? It's called lateral. It's called lateral. It's called lateral displacement. It's called lateral displacement. So take note of this. This place also, remember this is your angle of refraction. This place is your angle of deviation. So I is equals arrow plus D. Take note of this. But this is the refracted ray and this is the emergent ray, while this is the incidented ray. Now let's look at what we call read depth and apparent depth. Now let's imagine a pool has a read depth from the top to the bottom is the read depth. But someone having a view of the depth, the moment the light rays from the eye comes in contact with the water, this is water here, there is a bending of the light rays to now make the depth appear shallow. So this is the apparent depth, the fake depth. This is actually the real depth. So the depth is now appearing to be shallow. Meanwhile, it is really deep. Many persons have died in the pool because of this phenomenon. So now it means that from this point to the real bottom is displacement. So the land or the floor appears to be high. It's not actually high, it's really deep. So this is the displacement. From the top to this point is the fake depth or the apparent depth, while this is the real depth. Now, what is refractive index? In this format, refractive index is equal to real depth over apparent depth. Real depth over apparent depth. Now, let's put values. Let's assume our real depth is y and our displacement is x. Now, what does that tells you? It means and our apparent depth is z. It means this equation will be refractive index will be equal to real depth is y. It will be y over apparent depth is z. Now, I want you to know that it can still be equal to real depth, which is y, over real depth, which is y, over apparent depth can be, if this guy is not here, if z is not available, apparent depth can be y minus x will equals apparent depth. So apparent depth is y minus x. Take note of this. It means that apparent depth is equal to real depth minus displacement. Apparent depth is equal to real depth minus displacement equals apparent depth. Now let's look at this case, a case of a coin placed under a thick glass. So the coin is beneath the thick glass, and when the coin is viewed from the top of the glass, it is as though the coin is inside the glass. It can also be a write-up that will appear to be engraving inside the glass when viewed from the top of the glass. Now, what is this? We still know that refractive index equals real depth over apparent depth. But now, what is the real depth from? This is the real depth. So the real depth is our thickness. The real depth is our thickness. Then what is the apparent depth? This is the apparent depth, fake depth. While from here down is the displacement. This is the apparent depth, the fake depth. While this is the real depth, and the real depth is called thickness. So real depth over what is now apparent depth? Apparent depth is real depth minus displacement. Apparent depth is real depth minus displacement, which is now real depth. What is the real depth? Is thickness minus displacement. Look at it. Real depth over apparent depth. Apparent depth is thickness minus displacement because the real depth is it is thickness. The real depth is our thickness, which is from here to here, the thickness. Apparent depth is thickness minus displacement. That's our apparent depth. So I can further say that this is equals thickness over thickness minus displacement. If you cross multiply, you'll be having refractive index all over thickness minus displacement equals thickness. So this will not give you refractive index times thickness minus refractive index times displacement equals thickness. Take like terms, you have this go and this come. So this refractive index times thickness minus thickness is equal to refractive index times displacement. So thickness is common, open bracket, n minus 1 is equals refractive index. What is now displacement? Sorry, is equals n refractive index times displacement. What's now displacement? Displacement equals thickness. Let me take it up. Displacement is now equals thickness, open bracket, n minus 1 over n, and this can also be, this is equals thickness, open bracket, n over n minus 1 over n. This cancels this. Displacement is now thickness, open bracket, 1 minus 1 over n. Take note, all these are possible formulas you can use to solve, but remember, this is where it came out from. So now we have talked about real depth and apparent depth in terms of a pool, in terms of a coin. Now I'll be taking some questions to look through from refraction down to this point. Thank you. Now we'll be looking at questions from some exam bodies such as IGCSE, UTME, and SSCE. Number one says the speed of light in air is 3 times 10 raised to power 8 meter per second, and in glass is 2 times 10 raised to power 8 meter per second. Calculate the refractive index. Now, this is a question as regards speed. So, solution to this, solution refractive index equals speed in air over speed in glass. So refractive index is equals speed in air is 3 times 10 raised to power 8 over 2 times 10 raised to power 8. This takes out this. Refractive index is equal to 1.5. Note, refractive index has no SI units. Number 2 says, is the refractive index of glass with respect to air, refractive index of glass with respect to air. Now look at question number 2. Refractive index of glass. Refractive index of glass in respect to air is equal to refractive index of air over refractive index of glass. Remember, we have said this. This is how it's the reverse of the way you do both of speed and wavelength. Now, look at this very well. This is what they gave to us. So they are now asking us, what is the refractive index of air to glass? So if this is this, so it means that refractive index of air to glass would definitely be 1 over refractive index of glass to air. Look at this. It's very important. It's like something going straight and reversing. It's called the reversibility of light. So I have glass to air equals this. Air to glass will be the opposite of this. So that's why it is 1 over glass to air. So if I'm solving this, I have this to this is this to this is this. So it means that I have refractive index of glass to air is equal to 3 over 2. Therefore, what is now the refractive index of air to glass is equal to 1 over refractive index of glass to air. So it's equal to 1 over 3 over 2. So the answer of refractive index of air to glass is now equal to 2 over 3. That's the way that question is solved because it's a question under the reversibility of light. So air to glass, then glass to air. Now question number 3 says, a rectangular glass prism of thickness 12 centimeter is placed on a mark of paper resting on a horizontal bench. If the refractive index of the prism is 1.5, calculate the apparent displacement of the mark. Now remember, to solve question number 3, I'll be using refractive index is equal to real depth over apparent depth. That's what I will using to solve this question. Real depth over apparent depth. Now remember that refractive index is equal to real depth over real depth minus displacement. Apparent depth is real depth minus displacement. Now, remember, our question is asking us to find the apparent displacement. To solve my question, what is my refractive index? Is 1.5. 1.5 is equal to, what is the real depth? The real depth is the thickness. The real depth is the thickness. That's my 12. 12 centimeter over 12 minus d. So if you cross multiply, you'll be having 1.5 open bracket 12 minus d is equal to 12. So this becomes 18 minus 1.5d equals 12. So therefore, I have 1.5d is equals 6. So therefore, d is equals 4 centimeter. So the apparent displacement of this question is equals 4. Now let's look at question number 4. What's question number 4? We have a diagram that some certain parts were labeled and we are asked to find the refractive index of the question. Now you see from the top to the bottom is 10 centimeter. That's the real depth. Now the apparent depth, look at this point here. This point to this point is the apparent depth. But what was given us is y to z. So y to z is 4 centimeter. So it's the displacement that was given us, not the apparent depth. If you watch our previous video on this subject, you see that here to here is the apparent depth, not here to here. Here to here is the displacement. So now what is refractive index is equals real depth over apparent depth. But in a case where there's no apparent depth, what do we have? We'll now say that its refractive index equals real depth over real depth minus displacement. So refractive index is equals to real depth, which is 10, over real depth, which is 10, minus displacement is 4. So we have 10 over 6, which equal to 1 point. You have 4, then this into this. 1 point, you have 6, 7. 1.67. Thank you. Now let's look at question number 5. Question number 5 says, a ray of light incident at an angle of 30 degrees at an air glass interface. So it means the interface is an air to glass interface. This is the normal. This is light incidented, and it was done at an angle of 30 degrees. Take note, this is 30 degrees. Now the next thing is what will happen. Light moving from air to glass, it will bend away from normal. It will bend towards normal. It will bend towards normal. So This is my angle of refraction. Now, what is the question asking us to determine? The question is asking us to find the angle of deviation. Now, remember, this would have been the actual direction the light would have gone to. So, here to here is your angle of deviation. So, what do we have? We said angle of incidence, which is this angle, equals this two angle, equals angle of refraction plus angle of deviation. Now, the question is, do I have incident angle? Yes, I do. Do I have refracted angle? No, I don't. So how will I get my refracted angle? Because angle of incidence was, sorry, refractive index. The refractive index was given me, I would say, refractive index equals sine I over sine arrow degrees, which is not equal to, so I now have it as 1.5, look at it here, it was giving us, is equal to sine 30 degrees over sine arrow degrees. So this is 1.5 is equal to sine 30 is 0.5 over sine arrow degrees. If you cross multiply this, you have 1.5 sine arrow degrees equals 0.5. So I have sine arrow degrees equals 0.5 over 1.5. This will be this. So this is now 5 over 15, which will now be 0.33. Then I have what is now my sine arrow. My sine arrow degrees equals 0.33. Then arrow is now the sine inverse of my sine inverse of 0.33 becomes 19.45 degrees. This is our arrow degrees. Now remember that we have I equals arrow degrees plus D. So D equals I minus arrow degrees. So D is now equals angle of incidence is 30 degrees minus refracted angle is 19.45. So our final answer to this question will be 10.5 degrees. That's our final answer to this question. Now let's see the next one, which is question number 6. Question number 6 is a very funny question. Why? Because you see things very important here. This is incidented ray, this is a reflected ray, and this is a refracted ray. To solve this question, look at this straight line here. Look at this straight line here. Very important. I want you to look at that question very well. It's a very funny question. Look at it. There is a straight line here, and there is a ray here, and you have this, and then you have this. Just look at this straight line. Then you have this making an angle of 90 with this. So this is 90 degrees. Now remember that the angle of incidence is always equal to the angle of reflection. So this is a reflected ray. This is an incident ray, while this is a refracted ray. So I can tell you for free that this place will be 56 because I equals arrow from the law of reflection. Then if here is 90, I can find here, which is my unknown. I can find that part, which is my unknown. And this part, which is my unknown, is actually my angle of reflection. Is my angle of refraction, sorry. So this is my angle of refraction because refraction angle is the angle the refracted ray makes with the normal. So because it's a straight line, I will say 56 I'll say 56 degrees plus 90 degrees plus arrow degrees equals 180 degrees. So what is now arrow degrees? Is now equal to 180 minus, this will now be 146 degrees. So arrow degrees will now be equal to, that will be 34 degrees. Now, if our arrow is 34 degrees, what are we asked to look for? I'm asked to look for refractive index. So I'll say refractive index equals sine of incidence over sine of refraction, which is now equal to sine incidence is 56 degrees, sine 56 degrees over sine 34 degrees. Therefore, refractive 0.829 over 0.559. So refractive index is now equal to 1.48. So our refractiveness, the refractive index that was asked us to calculate for in this stage is equal 1.48. But take note of this. Note, I will solve it in another way. Anytime you see that your reflected ray makes an angle of 90 with the refracted ray. Anytime the reflected ray makes an angle of 90 with the refracted ray, you simply use this formula that refractive index is equal to the tan of the angle of incidence. So refractive index is equals tan. What is the angle of incidence? Is 56. So it's tan 56 degrees. This is equal to 1.48. This is what we call Brewster's law. Take note. I will only use this when the reflected angle makes an angle of reflected ray makes an angle of 90 with the refracted ray. That's the only time I'm permitted to use this formula instead of traveling this long a distance. Thank you. Now let's look at refraction in rectangular and triangular prism. Now let's take a case scenario of a rectangular box like this. Now light strikes. This is the angle of incidence. It bends. Why is it bending? Because it's moving from air to glass. So it bends towards the normal. So this is the angle of refraction. Now this is the incident ray. This is the incident ray. This is the incident ray. This is the refracted ray. Refracted ray. Then on getting here, something happens. It goes away from normal. This is the emergent ray. Very important to know this, that this angle is not the emergent angle. This is for a rectangular block. What about for a triangular prism? You have something of this magnitude. You have this. Now, if this triangle is an equilateral triangle, we said it has all sides equal. So A is the refractive angle of the prism. Light strikes. This is normal. It bends away from normal. Sorry, it bends towards the normal. Then this is another normal. Then it bends away from normal. Now please watch this very well. This is this against this. Now this gives us an angle here, which is A. This can go forward and this goes forward to meet at this point, and you have minimal deviation, which is dm here. Now take note, this is the normal, this is the incident ray. The angle formed here is called the angle of incidence. While this is the normal, look at the normal here. The normal, this is the refracted ray. The angle formed here is refracted angle. This angle here also is refracted angle. But the angle here is I minus arrow, while the angle here is I minus arrow. Now, this ray is the incident ray. This is the refracted ray, while this is the emergent ray. This is the emergent ray. Emergent ray. Take note of that. While here is the emergent angle. Now, what do we have here? I have two angles that I want you to see. What are the two angles I want you to see? I have something like this, and this. That's the upper part of it, where here is dm, here is I minus arrow, here is I minus arrow. Then I have another triangle. Look at it down, which is something like this, and something like this. This is A, this is arrow, and this is arrow. Now it is told us that I minus arrow plus I minus arrow equals minimal deviation. So I have I minus arrow plus I minus arrow equals minimal deviation. This becomes 2I minus 2 arrow equals minimal deviation. So I have, watch now, I have 2I minus 2 arrow equals minimal deviation. But in this case, I have arrow plus arrow equals A. Therefore, 2 arrow equals A. Arrow equals A over 2. So, what do I have here now? I want to make I the subject. So, I have 2I is equal to dm plus 2 arrow. What is arrow? A over 2. So, I have 2I equals dm plus 2 brackets A over 2. 2 cancels 2. So, I take it up here. I now have 2I is equals dm plus A. Therefore, I is equals dm plus A over 2. I equals A plus dm over 2. Now I've gotten my I. This is my angle of incidence, and this is my refracted angle. Now, if I come here, I will not tell you refractive index equals sine incidence over sine refraction. What is I? This is I. What is arrow? This is arrow. So therefore, I have my refractive index equals sine. In place of I will put open bracket A plus dm over 2, close the bracket, over sine arrow, which is now open bracket A over 2. This is a formula needed to solve for question in a triangular prism. Now, this is how it is being proved, and I just did that. But what is important is this formula: refractive index equals sine incidence over sine refraction, where the incidence is A plus minimal deviation over 2, and the refraction is A over 2. Now, what is A? A in this diagram is the refractive angle of the prism. For an equilateral triangle, it's 60 degrees all through. So A will be 60 if the triangle is equilateral. What is dm? Dm is minimal deviation. The minimal deviation that can occur when light passes through a triangular prism. What is my A? I've said that. Why this becomes my what now? My refractive index. So now I'll be looking at some questions as regards this diagram thing. Now let's look at a question like this that was tested in UTME and SSCE. Identify the following parts. So in this question, what is theta 1? Theta 1 is our angle of incidence. That's theta 1. Theta 1 equals angle of incidence. What's theta 2? Theta 2 equals emergent angle. Theta 2 equals emergent angle. What's theta 3? Theta 3 equals the refractive angle of the prism. That's A. Theta 3 equals refractive angle of the prism. That's A. Theta 4 is the same thing as the refractive angle of the prism. What about theta 5? Theta 5 is our angle of minimal deviation. Take note, at minimal deviation, I equals E. At minimal deviation, angle of incidence equals critical angle. But at maximal deviation, angle of incidence equals 90 degrees. Now let's look at this question. It says a glass triangular prism of refractive angle 60 degrees gives a minimal deviation of 47 degrees. What is the refractive index of the glass? I will be using refractive index equals sine I over sine arrow, which is equal to sine open bracket A plus dm over 2 all over sine open bracket A over 2. Remember, this is the formula for a triangular prism. So refractive index will now be equals the sine of open bracket. Refractive angle is 60 plus minimal deviation is 47 over 2 all over sine 60 over 2. Refractive index is now equal to sine of, this is 107 divided by 2 over sine of 30 degrees. So now we have refractive index is equal to sine of 50, 53.5 over sine of 30 degrees. So refractive index 0.803 over 0.5. So this will now be 1.6. That becomes the refractive index of the triangular prism. Thank you.